A scatter plot is a graph of ordered pairs, X and Y. For instance, this table shows the number of passing yards each game for a quarterback in column 1, and the number of points his team scored in each of those games in column 2. So passing yards is the X variable, and points scored is the Y variable. And these are ordered pairs of X and Y. And we can create a scatter plot for this data. Start by drawing an X and Y axis. Label the X-axis as passing yards and the Y-axis as points scored. Next, from the table, find the highest value in the table for X, which is 478. We can round up to 500 and mark that somewhere near the end of the X-axis. Then make 4 more marks of equal distances going down the X-axis, marking them 400, 300, and on down to 100. Next, from the table, find the highest value in the table for Y, points scored, which is 51. We can round up to 60 and mark that somewhere near the top of the Y-axis. Then make 5 more marks of equal distances going down the Y-axis, marking them 50, 40, and on down to 10. Next, we're going to plot the points on the graph. So, from the first row in the table, we have 256 as our X-axis value and 38 as the Y-axis value. Find that point of intersection on the graph and put a dot there. Next is 326 for X and 42 for Y, and we put a dot at that point of intersection. And when we continue this process for all 16 of the ordered pairs in the table, as I've done here. When looking at a scatter plot, one thing to take note of is the overall relationship between the dots, as you can have a positive linear relationship, a negative linear relationship, a curved relationship, or even no apparent relationship.
Correlation refers to a measure of how strongly 2 or more variables are related to each other. A positive correlation means that a high value of one variable are associated with high values of the other, while a negative correlation means that high values of one variable are associated with low values of the other. If there is no correlation between 2 variables, they are said to be uncorrelated. The strength of a correlation is measured using a correlation coefficient, which is calculated as a number between -1 and +1. If the number is close to +1, there is a positive correlation. If the number is close to -1, there is a negative correlation. And if the number is close to 0, then the variables are uncorrelated. When carrying out a correlation analysis, it is expected that the researcher will start with a hypothesis, which is a testable predictive statement. The hypothesis will state what the researcher expects to find out about the relationship between 2 variables. For example, that there will be a significant positive correlation between average exam scores and performance on a memory test. It is important that the 2 variables are clearly stated in the hypothesis. It's important to note that a hypothesis for correlation is a prediction of a relationship, and not a different or a cause and effect. Therefore, the researchers should be careful not to write a hypothesis for a correlation that includes the words difference, cause, or effect. When carrying out correlational analysis, the data is summarized by presenting the data in a scattergram or scattergraph. This enables the researchers to visualize any correlation that may be present, whether there is a strong positive correlation, a weak positive correlation, no correlation, a weak negative correlation, or a strong negative correlation. Correlations are very good for showing the possible relationships between variables, and sometimes they are the only practical or ethical way of carrying out an investigation. Researchers may use correlational analysis as a starting point for their research. If a relationship between variables is found, they can then investigate this further, perhaps using experimentation to investigate if there is a causal relationship. However, it is important to remember that a correlational analysis cannot demonstrate a cause and effect relationship between variables. For example, if we found a positive correlation between exam scores and attendance rates at school, we can't conclude that high attendance causes high achievement, or that low attendance leads to low achievement. It is possible that low achievement is leading to low attendance, and that low attendance is leading to low achievement, or that another variable, for example illness, is causing both low achievement and low attendance at school.
Which is most effective for helping people learn? Punishment or reward? Well, consider the case of Israeli fighter pilot training, because instructors there found that negative feedback was far superior to positive feedback. If a cadet performed a particularly poor maneuver, they would reprimand him, but they noticed that on follow-up attempts, his performance invariably improved. In contrast, if they praised a cadet for executing a skillful maneuver, his performance on subsequent attempts typically declined. So naturally, they concluded that positive feedback is ineffective or even detrimental, whereas negative feedback is what works. The problem is, this seems to contradict a body of research that shows positive feedback is actually more effective than negative feedback. For example, in studies involving teachers, it was found that if a teacher increases the ratio of positive feedback to negative feedback, that actually increases the percentage of time students spend on tasks. Well, so why didn't this work for the Israeli fighter pilots? Well, maybe there are cultural differences, and in some cultures negative feedback works better. Or maybe it's task dependent. Perhaps some skills, like learning to fly a fighter jet, require more negative feedback. Or maybe the feedback had nothing to do with the performance of the fighter pilots at all. Maybe they would have performed in the same way regardless of the feedback they received. Go with me on this. Imagine you have 100 students taking a test which consists of 100 true or false questions on a subject they know nothing about. Now, assuming they all answer randomly, we know that the resulting distribution of scores will have an average of around 50. But just by chance, some students will have scored significantly better or worse than the average. Man. If you select the top 10 students whose scores were all above 50 and gave them a second very similar test, you would find that the average of their scores would drop back to around 50. Similarly, if you selected the bottom 10 students, their score on a subsequent test would rise to 50. This is just regression to the mean. Regression to the mean is the reason why if you have a really good round of golf today, your round tomorrow will not be as good. Yes! That is because random chance plays a role in virtually everything that we do. So the outcomes of events are influenced by both our skill and a little bit of luck. So if you have especially good luck on one day, chances are your level of luck will not be as good the next day. Now that sounds a little bit like the gambler's fallacy, which states that past events influence future probabilities. For example, if you flip a coin and it comes up tails a couple times, the gambler's fallacy is to expect the probability of heads to increase for the next flip. In reality, it doesn't. It's still 50-50. The idea with the gambler's fallacy is that probabilities change so that overall things even out in the long run. That's the idea. With regression to the mean, it's not that things are evening out. It's just that extreme events are becoming diluted by the average events, which happen much more commonly. Now with these students, they were completely guessing on every question. But even when you know something about the subject, there's still going to be that element of chance. And so regression to the mean always occurs, just to a lesser extent. This is really important to consider in research. Imagine you're trialing a new drug to help prevent heart disease. So from a sample of patients, you select those in the bottom 10% of heart health indicators, people with high blood pressure, high cholesterol, and that sort of thing. Now, after a month of being on the drug, you test them again to find that their scores have improved. Well, great, the drug is working, right? Well, maybe not. See, the trouble is that although blood pressure and cholesterol are more stable than, say, your score on a random true or false test, there is still some inherent variability caused by, say, your level of stress on the day, or your recent diet, or even the uncertainties introduced by the measuring apparatus. So the people who ended up in the bottom 10% on the first test likely had these factors all count against them. They were particularly unlucky. But you should not expect them to be as unlucky when you test them a second time. So their scores should improve just based on random chance. That is why it is so important that clinical trials use control groups drawn from exactly the same population so that you can see whether the drug improves scores more than random chance alone would. Or what about assessing the impact of speed cameras? When they're first installed, they're normally put in locations that have had a high volume of accidents in the previous year or two. Makes sense? Now those accidents are likely due at least in part to bad road design, but also due at least in part to bad luck. And so you shouldn't be surprised that after a speed camera is installed, the number of accidents goes down. It would go down anyway simply due to regression to the mean. Meanwhile, somewhere else that previously had a small number of accidents will likely have more. So the overall accident rate may not change, and yet we will feel as though our investment in road safety has paid off. But perhaps what's most troubling about regression to the mean is how it influences our perception of feedback. For example, with the fighter pilots, after they execute a maneuver particularly poorly, chances are the next attempt is going to be better, regardless of the feedback they receive. Similarly, after an especially successful display, chances are the next attempt is not going to be as good. And that has nothing to do with the feedback and everything to do with the statistical nature of our universe. But we are hardwired to see patterns and causality everywhere, which is why the instructors felt that positive feedback was detrimental and negative feedback is what works. And this is really unfortunate because that is the exact opposite of what well-controlled psychological studies show. I think it's really unfortunate that if you give negative feedback, chances are you'll be rewarded. They will do better. And if you give positive feedback, chances are you'll be disappointed because it's difficult to maintain that level of luck. But that's the way our world is. So think about that next time before you tell someone off. If you stay positive, it may just work out for the best in the long run.
In 2003, Italian researchers published a scientific article claiming that eating pizza can reduce the risk of certain cancers. That's right, one of the most consumed foods on Super Bowl Sunday, greasy, cheesy, salty pizza is linked to fighting cancer. Newspaper headlines, online blogs, and editorials picked up on this astonishing study, creating headlines like, "Eating pizza cuts cancer risk," "Why pizza can fight cancer," and "Pizza reduces cancer risk." Now you may be thinking, can eating pizza really cut the risk of cancer? Is there a causal relationship between my favorite meat lover's deep dish and healthy living? Well, not exactly. You see, correlation does not imply causation. That is to say, if A is related to B, that doesn't necessarily mean A caused B. This is a common error in our thinking. Looking deeper into the research findings, there is much more than meets the eye. In this Psychedemia episode, I explore correlations, how two variables, yes, even pizza and health, are related. It is very tempting, and even exciting for food lovers, to read these aforementioned headlines and think that eating pizza can cause a reduction in cancer risk. But other scientists, and even the authors of the study, caution readers to quickly make a causal relationship. It turns out that a Mediterranean diet is more likely the cause of fighting cancer and healthy living. A diet that is rich in olive oil, fish, grains, fruits, and yes, tomatoes, one of the main ingredients on a pizza. Why does a correlation not imply causation? It is common to think that when two things relate to one another or appear linked, like money and happiness, violent video games and aggressive behavior, and eating breakfast and success in school, that one caused the other. But there are several reasons to be cautious. For instance, maybe there is a third variable. Oftentimes, two variables appear to be linked to each other, but in actuality, there is another unknown or third variable that is a real source of the link. This is called the third variable problem. Let's take a look at one of these examples. For decades, psychologists have investigated a link between first-person killing games, like Grand Theft Auto and Call of Duty, and aggressiveness in boys. One could argue that playing violent video games causes aggressive behavior. This argument supports why politicians in the past have tried to put an age limit on purchasing violent video games. However, one could also make the argument that a child who is already aggressive is more likely to seek out and play violent video games because it connects to their personality. Of course, what about a third variable? Some studies have shown that exposure to family violence, like spousal and child abuse, is associated with youth violence and an increased risk for playing violent video games. This finding reminds us that we should not jump to conclusions when establishing links between two variables. It is also very common for people to see relationships between variables when none exist, like eating candy and hyperactivity. This is called an illusory correlation. Let's take a look at a common example ubiquitous in sports: superstitions. Athletes are renowned for being superstitious. They often develop unusual rituals to keep hitting streaks alive or to end terrible slumps, for example. Anything to get the bad juju off their back, whether wearing the same lucky socks or eating the same meal before every game. From a psychological perspective, athletes have convinced themselves that a relationship exists between performing specific rituals and performing well on a field. Unfortunately, this relationship is merely a fallacy. So, why do psychologists conduct correlational research? Foremost, psychologists are interested in the relationship between two variables, specifically how well one variable predicts the presence or absence of another variable. Psychologists study relationships in all walks of life, like the relationship between attendance and GPA, money and happiness, intelligence and income, and depression and eating habits. Notice how the arrows are pointing in both directions. As I stated previously, this is because it's very difficult to make a causal relationship between two variables. Figuring out how closely two variables relate to or predict one another is measured using a statistical measure called correlation coefficient. This index measures the strength of a correlation. Represented by Pearson's R, the value of a correlation can range from positive 1.0 to negative 1.0, each being a perfect correlation. An R of 0 means no relationship exists between two variables. A correlation of positive 0.87, for example, will be considered very strong, while a negative 0.27 will be considered weak. Take a look at the following R values and identify the strength of each score. Think about the mistakes you made, if any, and rewind the video to clarify any confusion. It is important to note that positive doesn't mean good and negative doesn't mean bad, but rather positive and negative signify the direction of the correlation. Specifically, a positive correlation implies that one variable predicts the presence of another variable. In other words, as the value of one variable increases, the value of the other variable increases as well. For example, there is a positive correlation between the time you spend on a treadmill and the number of calories burned. In other words, the more you run, the more calories you lose. There is also a positive correlation between the amount of coffee you drink and level of alertness. The more coffee you drink, the more alert you will be in the classroom or office. Conversely, a negative correlation implies that one variable predicts the absence of another variable. In other words, as the value of one variable increases, the value of the other variable decreases. For example, there is a negative correlation between alcohol consumption and judgment. In other words, the more alcohol you drink, the less judgment one has. There is also a negative correlation between the amount of garlic in your home and vampires. The more garlic hanging in your kitchen, the less vampires will step foot in your house. Lastly, how do psychologists graph correlations? Correlations are graphed on scatter plots, like the one seen above. The slope of the scatter plot indicates the direction of the correlation, while the scatter of the data points indicates the strength. Each participant or event in a study is represented by a dot or data point on the scatter plot. The more scatter between data points, for example, would mean there is a weak correlation between two variables. The closer the data points are bunched together on the line of best fit would indicate a stronger relationship.
Well, hi there, boys and girls. This is Captain Kangaroo. Say, I'd like you to meet a friend of mine. So, you know, it's lots and lots of fun to have a pet that you can run and play and jump with, isn't it? But did you know that there are some boys and girls who can't run and jump and play? It's all because of a thing called polio.
When I think of bad historical assumptions about correlation and causality, I think of polio 100 years ago, when it was this horrible mystery that it was, claiming a lot of lives, and it was really scary because it mostly struck children. And there was a strong line of research that suggested that ice cream caused polio, that ice cream consumption caused polio.
Here comes Mr. Softy, the soft ice cream man. The creamiest soft ice cream you get from Mr. Softy.
The reason that correlation was thought to be causal was that polio spiked in the summertime for reasons that really weren't very well understood, but it did. And ice cream sales spiked during the summertime. So these researchers had seen that whenever there was a lot of ice cream being sold and consumed, there was a lot more polio. And so there was really literally the beginnings of this kind of ice cream persecution to try to stomp out polio. And it sounds ridiculous, but you see it all the time now, people trying to fight against or build up something that they're sure is connected to something else, in which it turns out just isn't.
In a research study, there is usually an experimental group and a comparison or control group. Those who are in the experimental group will get whatever's being researched in the study. Those in a control group will usually get the standard treatment for the condition. If there is no standard treatment, those in the control group might get a placebo that looks the same but is not intended to have the same effect as the experimental treatment, or they might get nothing at all. A control group is needed because people will naturally change a bit from one day to the next, even without being in a study. Some days people feel good, and some days they feel a bit worse. Sometimes just knowing they are in a study can change the way a person feels. Even some blood tests can be different from one time to the next because of things like diet, stress, hormones, or mood. And sometimes things can change without any known reason. Since everyone in a study will experience different natural changes, researchers can measure the changes in each person, add them together, and find the average change for each group. If the average change in all the groups is the same, then the changes in any one person, whether for better or worse, are probably due to natural variation and not whatever is being researched. However, if the average change in the experimental group is much better or worse than in the control group, it's likely that the new treatment is what's making a difference. A control group is used to help researchers know the difference between these natural changes and the true effects of whatever is being researched.
We are all capable of speculating about other people's behavior. We do it every day. That man who took my parking space is clearly arrogant and inconsiderate. That little girl screaming in the grocery store clearly has bad parents. But as normal as it is for us to make these kinds of assumptions and explanations, there is nothing reliable or scientific about any of it. Our spotty observations of little girls in grocery stores can't lead to any larger conclusion about the relationship between parenting and behavior. Psychology attempts to apply the scientific method to the study of human thought and behavior in order to reach conclusions that do have real explanatory or predictive power. Psychologists come up with a hypothesis about people, that overly indulgent parenting leads to temper tantrums, for example, and then try to design a study that will show it to be right or wrong. There are many different kinds of studies, but all face the common problem of separating out the behavior you want to study from all the other kinds of behaviors that might happen along with it, and the potential cause from other things that could cause it. Let's say you want to design a study to see whether parents who give into their child's every wish are likely to have children that will have tantrums. You might ask parents to fill out a questionnaire to determine their parenting style. You then ask those who were especially indulgent and permissive to bring their child in to participate in a test of their ability to solve math problems. You tell them they'll get a candy bar as a reward for doing well. You don't really care about the children's math ability, that's just the pretense for getting them into your study. What you really care about is their behavior during the test. When they've finished, you look in your desk and then, in mock surprise, say, "Well, it looks like we're out of candy. Let me go ask a colleague if he has any." You leave the room for about 5 minutes, come back still empty-handed, and apologize for not having any candy. Though some of the children seem disappointed but okay, many of them start to cry and demand candy. Once you've taken note of the reaction, you have a friend run in breathlessly with the last candy bar, and the children leave your study munching happily. You take a look at the numbers. 80% of the children exhibited some kind of tantrum behavior when they found out they weren't really getting candy. You conclude that, just as your hypothesis stated, indulgent parents are associated with bratty children. If you stopped here, you would have ignored one of the most important ideas in scientific testing, the scientific control. Your study design does seem to distinguish between different potential behavioral reactions to a common situation. Some kids cry and others don't, but your study doesn't distinguish between potential causes. All of these children have indulgent parents, but you can't be sure that it's indulgent parenting and not some other factor that causes 80% of them to cry. To help determine this, you'd have to bring in an equal number of children selected randomly and submit them to the same test. This is your control group. You find that about 80% of these kids cry as well when they're denied candy. This means that your original conclusion that indulgent parenting is associated with bad behavior is actually not supported by the results. All you can really say is that being denied promised candy makes a significant portion of all children cry. There are two possible explanations for this. One is that parenting style has nothing to do with behavior. The other, perhaps more likely explanation is simply that your study upsets children too much to learn anything valuable from it. Think of some tests you've taken. Some are really easy, like a math test in which the only question was 1 plus 1, and everyone who takes them gets 100%. Getting 100% on the test doesn't have very much to do with your preparation or your intelligence. It has more to do with the question being really easy. But if you're given a harder math question, like finding the integral of 2n, your score means more. If only a few people are getting 100%, this probably means that they have prepared better than everyone else. Promising kids candy and then refusing to give it to them is like the really easy test. Most of them cry, but that's probably just because it's a really upsetting situation. If you designed a milder scenario that didn't cause as many tantrums, it might be able to tell you more about the differences between children who still did have tantrums and those who didn't. This parenting style / children's behavior / candy bar test is made up, but it should give you some idea of the questions that psychologists have to ask themselves when designing studies and interpreting the results. The principles of the scientific method are very important for psychologists, who come up with hypotheses about behavior and then try to prove them right or wrong. Scientific control is crucial to getting results that sufficiently pull apart different potential behaviors and causes.
Two ideas that often get confused in looking at experiments and subject selection and subject assignment are random sample and random assignment. Random sample is the process of choosing the research participants. So whether you're selecting for a survey or selecting for an experiment, you choose randomly. This hopefully will give you some level of representativeness in the process. It certainly increases the likelihood. And this happens before the experiment or before the survey is actually done. And then in an experiment, if you also have your groups, your control group and your experimental group, their sample subjects will be divided into either the control group or the experimental group. And this is going to be random assignment. Each participant has an equal chance of being placed into any group, whether it's placement into the experimental group or into the control group. And this happens after the random sample.
Psychologists use experiments to investigate how manipulation of one factor causes a change in another factor. Scientists refer to these factors as one of two kinds of variables. The independent variable is that first factor, the one whose influence we're trying to measure. An independent variable doesn't change based on the other variables. The second factor, the one being influenced by changes, is called a dependent variable. This kind of variable changes based on the independent variable. Experiments are the best way to determine cause and effect relationships between these variables. Psychologists rely on random assignment to assign subjects to different groups in an experiment. Random assignment leaves it completely up to chance to determine which subjects receive the critical part of the experiment, which is imperative for determining that the independent variable is indeed what creates the result. Randomly assigning subjects helps to eliminate confounding variables or variables other than the independent variable that could cause a change in the dependent variable. Suppose one day while studying for a test, you notice that you seem more focused and productive while you are listening to music. In fact, you think it's possible that listening to music while studying helps you earn better grades on tests. You have been taking psychology courses, and armed with the love of science, you decide to conduct an experiment to see if your hypothesis is correct. You decide to test your hypothesis on the 300 students in your college introduction to psychology class. What is the independent variable in your experiment? Remember that the independent variable is the part of the study that is manipulated or changed to determine a result. In your experiment, you will manipulate whether or not students listen to music while studying. So listening to music is the independent variable. The dependent variable then will be the subject's scores on the test. The dependent variable shows the effect of the manipulation. To test the independent variable, you will need an experimental group and a control group. The experimental group is the group who receives the critical part of the experiment, the treatment. This is the group who will listen to music while studying. But to know if the music has an effect on test scores, you will also need to compare the results of the experimental group to a control group, a group which doesn't receive the critical part of the experiment. In this case, our control group won't listen to music while studying. How will you decide who is in the experimental group and who is in the control group? What about allowing students to choose which group they're in? No, that won't work. Maybe the students who choose to listen to music are already better students who excel at focused studying. We can't assume the results will be valid. Okay, so how about picking the experimental group based on a first-come basis? Sorry, choosing to put the first 150 students who come to class in the experimental group is also not random assignment. Maybe those students who get up earlier to make it to class on time typically perform higher on tests because they get more sleep. Random assignment is the only way to eliminate other variables that could influence your results. So, how do you ensure random assignment? There are a lot of different methods. The only requirement is that every subject has an equal chance to be in the experimental group. Drawing names out of a hat or creating a lottery are ways to make assignment to the experimental group random. Choosing every third name off a list of students is also random. Several computer programs can generate a random assignment of participants for you. The important piece is that subjects are equally likely to be in the experimental group. Random assignment is the best way to assure that the only difference between the control group and the experimental group is whether or not they receive the treatment. Any other differences between groups, such as amount of sleep, GPA, or even unknown factors, are more likely to be equally distributed if subjects are chosen randomly. Random assignment is the only way to assume the difference in test scores is caused by listening to music while studying. It allows psychologists and budding psychologists like yourself to have confidence that the results of your study are valid. In psychology experiments, psychologists use random assignment to assign subjects to groups. Using random methods, subjects are assigned to either an experimental group, which will receive an experimental treatment and observed, or the control group, which is observed under normal, non-experimental conditions. Random selection ensures that there will be no confounding variables or factors that could influence the result of the experiment. Confounding variables can render an experiment's finding completely invalid. There are many ways to assign subjects completely randomly. You can use a computer program, take names from a list at regular intervals, or even pick names from a hat. The important thing is that a random assignment method must allow every subject an equal chance of being in either the experimental group or the control group.
So we decided to do a single blind study for our caffeine and reaction time experiment. So in a single blind study, the researcher knows what group the participants are in. There's another way that we can reduce bias in a study, and that's by doing a double blind study. So in a double blind study, neither the researcher nor the participants know what group they're in. This will further reduce bias by controlling for experimenter expectancy effect. For example, let's say instead of looking at caffeine's effect on reaction time, we want to look at the effects of kindness. Well, maybe I, as a researcher, believe that caffeine does make people more friendly. Well, when I interact with the subjects to rate their kindness, the belief I have may cause me to be more friendly towards them, which may in turn make the subjects more friendly to me. So my inconsistent treatment between the two groups may result in an unintentional bias, and that can affect the results of my study.
In 1996, 56 volunteers took part in a study to test a new painkiller called trivaricaine. On each subject, one index finger was covered in the new painkiller, while the other remained untouched. Then, both were squeezed in painful clamps. The subjects reported that the treated finger hurt less than the untreated one. This shouldn't be surprising, except trivaricaine wasn't actually a painkiller, just a fake concoction with no pain-easing properties at all. What made the students so sure this dummy drug had worked? The answer lies in the placebo effect, an unexplained phenomenon wherein drugs, treatments, and therapies that aren't supposed to have an effect and are often fake miraculously make people feel better. Doctors have used the term placebo since the 1700s, when they realized the power of fake drugs to improve people's symptoms. These were administered when proper drugs weren't available, or if someone imagined they were ill. In fact, the word placebo means "I shall please" in Latin, hinting at a history of placating troubled patients. Placebos had to mimic the real treatments in order to be convincing, so they took the form of sugar pills, water-filled injections, and even sham surgeries. Soon, doctors realized that duping people in this way had another use: in clinical trials. By the 1950s, researchers were using placebos as a standard tool to test new treatments. To evaluate a new drug, for instance, half the patients in a trial might receive the real pill. The other half would get a placebo that looked the same. Since patients wouldn't know whether they'd received the real thing or a dud, the results wouldn't be biased, researchers believed. Then, if the new drug showed a significant benefit compared to the placebo, it was proved effective. Nowadays, it's less common to use placebos this way because of ethical concerns. If it's possible to compare a new drug against an older version or another existing drug, that's preferable to simply giving someone no treatment at all, especially if they have a serious ailment. In these cases, placebos are often used as a control to fine-tune the trial so that the effects of the new versus the old or alternative drug can be precisely compared. But of course, we know that placebos exert their own influence too. Thanks to the placebo effect, patients have experienced relief from a range of ailments, including heart problems, asthma, and severe pain, even though all they'd received was a fake drug or sham surgery. We're still trying to understand how. Some believe that instead of being real, the placebo effect is merely confused with other factors, like patients trying to please doctors by falsely reporting improvements. On the other hand, researchers think that if a person believes a fake treatment is real, their expectations of recovery actually do trigger physiological factors that improve their symptoms. Placebos seem to be capable of causing measurable change in blood pressure, heart rate, and the release of pain-reducing chemicals like endorphins. That explains why subjects in pain studies often say placebos ease their discomfort. Placebos may even reduce levels of stress hormones like adrenaline, which can slow the harmful effects of an ailment. So shouldn't we celebrate the placebo's bizarre benefits? Not necessarily. If somebody believes a fake treatment has cured them, they may miss out on drugs or therapies that are proven to work. Plus, the positive effects may fade over time, and often do. Placebos also cloud clinical results, making scientists even more motivated to discover how they wield such power over us. Despite everything we know about the human body, there are still some strange and enduring mysteries, like the placebo effect. So what other undiscovered marvels might we contain? It's easy to investigate the world around us and forget that one of its most fascinating subjects lies right behind our eyes.
Does the color of a car affect how fast you drive? A psychologist, for example, might hypothesize that participants given a red car, as opposed to a blue or green car, may drive faster because seeing red can increase your heart rate and cause an adrenaline rush. But the purpose of this video is not to argue whether color would or would not cause somebody to drive faster, but rather to understand and break down the variables that make up a study, specifically the independent and dependent variables. So let's dive in. All right, so let's first understand the design of the study. A psychologist randomly assigns participants to 4 conditions: a red car, a blue car, a green car, and a white car. And each participant is told to drive around an empty racetrack 50 times. And the average speed in miles per hour is recorded. So there's the design of our study. Now, to identify the independent and dependent variable, let's first understand what we mean by variables. This is a term we hear in biology and physics and chemistry and, of course, psychology. But what does it actually mean? The reason we use the word variable is because there are things within a study that can vary. Vary meaning change, right? Think about your life. Your mood can vary, right? One day you're happy, one day you're sad. The weather can vary. One day it's cold, one day it's hot. And what we want to know in a study is what are the things that have the potential to vary or change? Let's take a look at our question again. Does the color of a car affect how fast you drive? So what are the things within the study that can vary or change? Well, the color can, right? We have 4 different colors: red, blue, green, and yellow. And of course the speed, right? You could drive slow, you could drive fast. So those things become the variables. Now the question is, what is the independent and what is the dependent? Let's start with the independent variable. Now the first thing I want us to do, before we dive into specifically what it is think about everything that could affect how fast you drive. Let's list a few of them. One of them might be the type of car you own, right? If you're driving a minivan versus a sports car, that could affect how fast you drive. Your mood, right? If you're happy, sad, angry, right? That could affect how fast you drive. The weather, as we said before, if it's snowy, if it's rainy. Your age, right? If you are, an experienced driver or you're a new driver. If there's traffic on the road, you're going to drive slow, you're going to drive fast, you're going to weave through traffic. And we can go on and on and on. But these are some variables that might affect how fast you drive. But let's go back to our question. Does the color of a car affect how fast you drive? So color is also a variable. So all of these represent variables that could impact how fast somebody drives. But what do we want to know? We don't care about the weather. We don't care about your age. We don't care about the type of car. What do we care about? We care about the color and the color alone. And the reason we call this the independent variable is because we need to make this variable independent or separate from the other variables, right? We got to separate it. We can't have it along with the other ones. And that is why the independent variable would be the color of the car. And all these variables, what do we do with all those variables? Well, these variables have to remain constant. In other words, the only variable that can change in the whole study is the color. And everything else must remain unchanged. In other words, we have 4 conditions: red car, blue car, green car, white car. Every one of these variables, other than color, has to be exactly the same in every condition. In every condition, the weather has to be the same. Let's say it has to be sunny the whole time. The traffic, there's got to be no traffic, which is why I said an empty racetrack. The type of car, I can't have one person driving a minivan and another person driving a sports car, so the car has to be the same in all of those. So there we go. That is our independent variable. It is the one that you manipulate. It is the one that you change. It is the one that is the cause or treatment, and everything else must remain unchanged. So what would be our dependent variable? Well, our dependent variable depends on the independent variable. So what does that mean? Let's break that down. What we want to know is how fast somebody's driving, right? We have to collect some sort of results and analyze. The dependent variable is the data and results that you collect to see if the color even makes a difference. So where are we collecting the data from? We're collecting the data from the speed at which people drive, which is why the speed in terms of miles per hour would be our dependent variable. So let's think about this in a sentence. The speed is dependent on the color of the car. So we have the color independent of the other variables and speed being dependent on the color. So instead of, let's say, manipulate, treatment, and cause, we have things like the dependent variable we consider the results. The results or outcome, or what you measure. Or in this case, a nice memory technique would be this is the data. So a nice way to remember it is think about D, dependent data, DD, dependent data. And instead of the cause, we have the effect, cause effect. So this is just a nice way to distinguish the dependent and independent variables. All right, so what if you actually wanted to see the results of the study, right? How do we know if the independent variable had some impact on the dependent variable? In this case, does the color of a car impact how fast somebody drives? Well, here's kind of a general rule of thumb. The independent variable will always be on our x-axis, and our dependent would be on our y-axis. So we have our horizontal line, this would be our x-axis, and our vertical line would be our y-axis, right, colors and our speed. And let's just do some sort of hypothetical, right, bar graph. We have our, red going up here, right, miles per hour. There's 1. Here's blue down here. And then what we want to know is, what was the average miles per hour, right? Red, maybe it was 38.2 miles per hour, right? And maybe blue was, 10.5 miles per hour, and green was 13.6 miles per hour, and white maybe 15.5 miles per hour, right? And then you can actually conclude or make some inferences from those results. Remember, the independent variable is the variable that you isolate and separate and keep independent from the other variables that you remain constant and unchanged. While the dependent variable depends on the independent variable. It's the numbers, right? It's the measurement, it's the data that you collect to see if the independent variable had any effect at all.
Okay, by now you should be familiar with the procedure and vocabulary involved in an experiment. Terms such as trial, random assignment, control group, experimental group, and independent and dependent variables should be second nature to you. And you should be aware that an experiment is designed to determine the effect of an independent variable on a dependent variable. Now, in a perfect experiment, only the independent variable would have any effect on the dependent variable. But alas, life and experiments are rarely perfect. Extraneous variables are often present in an experiment and may or may not compromise the validity of the experiment. An extraneous variable that affects the validity of an experiment is referred to as a confounding variable. Now, to better understand what I mean, let's take an experiment that's been done in grade schools for generations. Let's see whether sunlight makes plants grow. You start your light growth experiment by placing one plant in the sunlight and one in the darkness, and then you wait. When you see that one of your plants is doing better than the other, you automatically assume that it's due to the sunlight, but you may be wrong. Did you accurately measure the water given to each? Or how about the soil and air temperature, or the size of the containers, and even the location? These are all extraneous variables, extra variables that may or may not interfere with your experiment. Now, if any of these extraneous variables impact your results, then we call it a confounding variable. Think of all the extraneous and confounding variables that may be present in a psychological experiment, especially those involving humans. Then you'll get an idea of why it's so important to recognize extraneous variables, especially the confounding ones.
The Hawthorne effect is the tendency we have to perform better when we know somebody is studying us. For example, a 2015 study of hospital staff hand washing found that staff were almost 3 times more likely to wash their hands when they knew they were being studied. The term Hawthorne effect comes from an experiment conducted at a US factory run by General Electric in Hawthorne near Chicago during the 1920s into factors that affected productivity. Everything worked. Increasing the illumination of the factory boosted productivity. Dimming the lights boosted productivity. Introducing rest pauses also worked. So did small group incentives. Oddly, after a positive change, returning to previous work conditions was also met with positive results. One popular interpretation of these results is that the novelty of being observed leads humans to perform tasks better. When we feel we're being studied, we improve our behaviour. While the experiment has been described as a glorified anecdote and it certainly falls well short of modern social science, it gives rise to this famous Hawthorne effect. Modern studies have confirmed the presence of this effect in a range of scenarios. In my own work, I've had participants literally say, "I was going to do A, but I knew you were coming in, so I did B." This can be a cause of frustration for researchers. When humans know they're being studied, their performance usually improves. That is the Hawthorne effect.
Designing a psychological study isn't really that hard. If you've ever written a survey or taken a poll among your friends, you've conducted some crude psychological research. But designing a study that produces valuable and scientific results is really challenging. If you gave your friends a survey about their political leanings, they might be influenced by the way you phrased the questions or by knowing your own political opinions. Your survey might not accurately measure what you think it does. Two key components for designing scientific psychological studies are reliability and validity. We'll look at some examples of both to better understand the importance of careful research design. Do you have a friend or family member who will always help you out if you ask? You'd probably describe this friend as reliable. Reliability in psychological research isn't really that different. It means that your tools for measuring a given variable measure it accurately and consistently. If you use a rigid ruler to measure the length of your foot, you should always get the same length. This is a measurement that has test-retest reliability. But if instead you measure your foot by holding your fingers about an inch apart and then moving them down the length of your foot and counting as you go, you'd probably come up with different measurements each time. Your fingers are not a particularly reliable measurement tool for the length of your foot. Important to designing and interpreting psychological research is the idea of validity. In general, validity refers to the legitimacy of the research and its conclusions. Has the researcher actually produced results that support or refute the hypothesis? It can be easier to understand validity by looking at some of the ways that research can be not valid. A study fails construct validity if what it chooses to measure doesn't actually correspond to the question it's asking. Let's say you were doing research that required you to know how intelligent your subjects were. To measure intelligence, you decide to administer a really difficult physics exam. If you did this, your experiment would lack construct validity because a score on a physics exam doesn't really measure intelligence. It just measures whether you've taken physics or not. Internal validity has to do with confirming that a causal relationship you've found between your variables is actually real. Even if you think you've found a definite relationship between changing one variable and observing change in another, you could be inadvertently changing something else that is actually causing the effect. As an example, let's say you wanted to test whether certain colors of fonts help people remember information better than others. You give your subjects two texts, one in green and one in red. The red text is about celebrity gossip. The green text is about chemistry. You find that your subjects remember the red text much better and conclude that red font helps memory. But by having two different texts, one much more easily memorable than the other, you introduced a confound into your experiment. You don't know whether your effect is caused by the red font or by the more interesting content. A third type of research validity is external validity, which has to do with your conclusions applying to more people than just the ones you tested. Though psychologists might like to test everyone, doing so would be absurdly expensive and time-consuming. So instead, psychologists take a sample of the population they want to study. This sample group is usually selected at random, based on who volunteers to participate. Psychologists try to get bigger groups to control for random variations. Usually, the results found in the sample are assumed to generalize, unless there are compelling reasons to question it. For example, if a study on attitudes toward aging had only college students for subjects, it might fail external validity. In general, reliability and validity are principles related to making sure that your study is actually testing what you think it is. Reliability makes sure that your test measures its variables accurately. Validity ensures that your measures and variables are telling you what you think they should, that your questions assess the right variables, that your experimental results have no confounds, and that your results generalize like you think they will.